So in this video, I'm just going to be working through a bunch of examples of differential equations. So we'll just get right into it. So there's really two types of differential equations we'll be doing in this class. There's the differential equation like these, where you're just finding a general solution, which means basically means we won't replace the c. We won't find out what c is. The second type of differential equation is called initial value problems, where you have a differential equation and you have some information about the solution. So in other words, y of, in this case we're saying y of x is the solution to that differential equation, and we happen to know that when you plug in 1 into that function, you get out 1. So these are called initial value problems. So you solve the differential equation to get the general solution, and then you use this part, this extra information, to actually find out what c is, so we can narrow it down to just one function. So in the first video you watched, we were given an acceleration equation, and we solved that, and we thought of it as the differential equation because acceleration is the derivative of velocity, and then we knew something about the initial velocity. So we were doing initial value problems at the first part of that video, and then the second part of the video I just solved one for a general equation. So let's go back and do this. So the technique for solving differential equations that we're learning here is just the separation of variables. So in this case, it's pretty easy. I just move dx to the other side. So that's 5x dx. Then I integrate. Integral of dy is y. Integral of 5x dx would be 5 over 2 x squared, and then plus c. And that would be it, because you already have y by itself. Because usually the end result of these general form equations is that you want to get y by itself. You want it in explicit form. So that would be your answer for that one. Now this second one, notice that there's just a y here, no x. So nice. When I separate variables, I'm going to have to divide by y. So that'd be dy over y is equal to 5 dx. And then I'm ready to integrate. So I integrate. Integral of dy over y, of course, is just natural log of y. The integral of 5 dx would be 5x plus c. And then to get y by itself, if you remember from pre-cal, we exponentiate, which means I make both sides a power of e. So that would be e to the ln y and e to the 5x plus c. Of course, e to the ln y is just y. And e to the 5x plus c, as we talked about in the first video, this would just be c times e to the 5x. Because remember, if I have e to the 5x plus c, that's the same thing as e to the 5x times e to the c, because when you multiply powers, you add their exponents. And e to the c is just a constant, so we just, maybe we should call it k or something, just so you know we've changed. We're not saying that this is the same as that, but we're saying it's still just some constant. So, okay, number 3. Looks like there's no y's on this side, so I just got to get the dx over. So that's dy is equal to x squared plus 4 dx. And I integrate both sides, and I get y is equal to 1/3 x cubed plus 4x plus c. And y is already by itself, so I'm good. This one here, now this poses a small problem, because we have y squared plus 5, and you can't just subtract y squared from both sides, because then you'd end up with a negative y squared plus dy, and having plus dy doesn't work for integration. So what we're actually going to have to do here is, we're going to have to divide both sides by y squared plus 5, so that'd be dy over y squared plus 5 is equal to dx. And this poses a problem, because it creates a differential equation that we are not able to, well, this class is not able to solve. Or I'm sorry, it proposes it makes So when we go to integrate both sides, it makes an integral that this class is not ready to integrate. So we're not, until we learn some future techniques, this is not going to be integratable. Okay, so moving on. This one here is when I separate variables, I get dy over y is equal to x dx, and I integrate both sides, and that would be natural log of y is equal to, whoops, I forgot to put the absolute value in there. Yeah. And that integral of x would be 1/2 x squared plus c. And we exponentiate both sides, and we get y is equal to k times e to the 1/2 x squared. And here's another one, similar to the one up above. This one we are going to be able to handle, though. So when I integrate both sides here, of course on this side I get x plus c. On this side, this is actually the natural log of y plus 4. And then we exponentiate both sides, we get y plus 4 is equal to k times e to the x. That means y is equal to k times e to the x minus 4. Okay, these last 4 problems, these are the initial value problems, so there's a kind of a 2-step process to them. Once again, we separate variables, so that would be dy is equal to 2x dx. Integrate both sides, and you get y is equal to x squared plus c. Now, normally we'd be done in the previous problems. That was the end of the problem, because there's we got y by itself, and this is just a general form. So this, if you think about it, represents a family of equations, of solutions, I mean, because I could replace c with any number, and what this is suggesting is that it would work for that differential equation. But what we're saying is we want a specific one from that family that when you plug in one, you get out one. So that means I can go over here and say, okay, let's say that y is equal to 1, which means, according to this, x would have to be equal to 1. And then we can find out what c has to be. Well, in this case, c would be 0. So the solution to this initial value problem is going to be just y equals x squared. Because notice when you plug in 1 for x, you get out 1. And if you plug in, if you take the derivative of x squared, you get 2x. And if you replace that with 2 times x squared, well, let's just show that it works. So we have dy dx is equal to 2x. So I'm going to replace dy dx with the derivative of that. That'd be 2x. And that is just 2x, right? Just replace that. Okay. So this one's kind of a cute one. First thing you want to do is separate variables again. So I have dy over y is equal to, and I'm just going to leave the 3 here and multiply it through. So that would be 3x minus 3 dx. So then I integrate both sides. I get natural log of y is equal to 3/2 x squared minus 3x plus c. Integrate both, or exponentiate both sides, and I get y is equal to k times e to the 3/2 x squared minus 3x. 2 more here. Oh, wait, we haven't done this yet. We got to find out. Oh, this says that when y equals, when x equals 0, y is 5. So let's take this right up here and do it. So that would be the natural log of 5 is equal to 3/2 times 0 squared minus 3 times 0 plus c. So that means that the natural log of 5 is equal to c. So then k is going to be, so then let's redo this. So now c is natural log of 5. So then I get when I exponentiate both sides, I get y is equal to e to the 3/2 x squared minus 3x times e to the natural log of 5. And of course, e to the natural log of 5 is just 5. So that'd be y is equal to 5 times e to the 3/2 x squared minus 3x. Okay, 2 more problems here. We're going to separate variables once again. When I separate variables, I get dy over y minus 2. And over here, I get x over x squared dx. So before I integrate, I'm going to rewrite that as 1 over x dx. And so then when I integrate both sides, I get natural log of y minus 2 is equal to the natural log of x plus c. And the way I exponentiate both sides, so that would give me y minus 2 on this side and just x on that side. No, it wouldn't. It would give me, well, let's be careful. It would give me e to the ln of x plus c, which would be equal to which would be equal to y minus 2. That would be e to the ln x times e to the c. And of course, e to ln x is just x. So then we'd have y minus 2 is equal to x times e to the c. And we know from up here that when x equals 1, y equals 5. So I'm going to replace x with 1 and y with 5. And I get 5 minus 2 is equal to 1 times e to the c. That means 3 is equal to e to the c. So then I can, this is going to be y minus 2 is equal to 3x, which finally we get y is equal to 3x plus 2. Okay, one last one here. If we separate variables, we get dy over y is equal to dx over x. Integrate both sides, and we get natural log of y is equal to natural log of x plus c. We could plug in right there right now, and you can plug in to find out c anytime after you've integrated. You know, I've been doing it at different times, but so in this case, I'm going to get what if I plug in 2 for x and 3 for y? That would be natural log of 3. Natural log of 3 is equal to natural log of 2 plus c. So that means that natural log of 3 minus natural log of 2 is equal to c. So, of course, we can rewrite that as natural log of 3 over 2, can't we? If we remember our log rules. So then I have natural log of y is equal to natural log of x plus natural log of 3/2. So I exponentiate both sides. I get y is equal to 3/2 x, because this would be e to the something plus something, which means something's multiplied. All right, that's a video on differential equations, solving differential equations, both with initial value and without initial value, which means we just get a general solution.